Hello everyone, my name is Felipe Gonzalez and I am a project scientist at UC Berkeley, and today I'm going to present a model that we have developed from ab initio simulations to understand ramp compression experiments. I would like to start by acknowledging my collaborators, my funding sources, the DOE and the Center for Matter-like Extreme Conditions, as well as the computational resources provided by the NERSC facilities. So our main motivation is to understand ramp compression, to understand what happens with a material as it's ramp compressed and what are the thermodynamic states that it visits as the pressure increases. In particular, we are motivated by earlier experiments on diamond that showed that one can reach up to 5,000 gigapascals in these experiments. More recent experiments from last year confirm these stress density measurements and made some models that allowed them to predict what the temperature was on these experiments. But you can see that there's a very large uncertainty on the predicted temperature, and this is mainly due to this factor called the Taylor-Quinney factor, or beta, that accounts for the amount of plastic work that goes into heating the sample. And this is largely unknown. Now, from a theoretical point of view, we realized that we had a really hard time explaining these measurements because we could not find any stable thermodynamic state that was compatible with these values of stresses and densities. And I will explain more details in the next slides. And that's why we felt the need to develop a model that provides a mechanism that explains how energy and temperature increase as the material is ramp compressed. Now, you may think that there's something wrong with our simulations, but as a matter of fact, if you look at the Rankine-Hugoniot curve predicted by ab initio simulations, which is the black line here, it agrees remarkably well with the experiments on shock compressed diamond, not only in the solid phase, but also in the liquid phase, and even when the liquid goes up to pressures of 2000 GPa. So we do not think that our simulations are flawed in any sense. They are capturing the equation of state of diamond really well, so the problem must be somewhere else. Now, if we look at this data, we can observe that there's an offset of more than 500 GPa between the cold curve of diamond and the measured stresses, so there must be a temperature difference between these two states. And one explanation could be that the sample actually melted. But the problem is that if you take the equation of state of liquid carbon and you assume that the reported stresses are the hydrostatic pressure of the liquid, then the temperatures that you inferred for every density and pressure are actually higher than 20,000 Kelvin, which is the line that we report here. But there are actually good reasons to believe that in the experiment the sample did not melt, it stayed solid, and having temperatures between 20 and 40,000 Kelvin for those densities and stresses may not seem plausible. What we tried next was to subject the solid to really high values of uniaxial strain to increase the stress in the compression direction. We tried with both the diamond and the BCA phases of carbon, and we picked a density around 10 grams per cubic centimeter and a temperature that was just below the melting temperature. At this temperature and density, the isotropic pressure that we get is 2500 GPa. And when we start doing the uniaxial compression, keeping the density constant, just adjusting the shape, we obtain values of the stress in the compression direction that are 300 GPa higher than the original isotropic pressure. But that is still not enough to reach the values of the stress reported at that particular density between the error bars provided. We also tried incorporating porosity, which was originally included in the experiment, but that actually went the other way around in the sense that it is even harder to get a higher value of the stress in the compression direction when the sample is porous. So far, there have been 3 experiments that have ramp compressed diamond to the megabar regime. One by Bradley et al. That took diamond to 800 GPa in 2009 and have some estimates for the temperature reached in those experiments based on plastic work models. And the experiments that I just mentioned that reached 5,000 GPa and 2,000 GPa more recently. But in none of these experiments, the temperature was measured. Basically because temperature measurements in ramp compression experiments are really challenging, and there's no way or equation that we have that can allow us to predict what the temperature was in a ramp compression experiments as we could do for shock compression experiments. So this leaves many open questions like, what is the equation of states of diamond that we are using? Are we modeling it correctly? What are the strength effects? Are the models for strength valid at these extreme conditions? What is the actual amount of plastic work that is going into heating the sample? And is ramp compression really isentropic in the solid? We believe it is, but we don't have evidence of temperature that the compression is following an isentropic path. So I want to address this question of what is the thermal state of diamond during ramp compression that would allow us to answer all these questions. There have been efforts to measure the temperature in ramp compression, like the XAFS technique on iron, and also models that have been developed to infer what the temperature could have been in the experiments. But as you can see, the error bars are very large in the measurements, and the uncertainties are also very large in the models. So this does not allow us to claim that the compression is really isentropic, or which isentrope the material is following. And this would be great if it was isentropic, because we know that the convective interiors of planets are isentropic, so we would be probing the interior of a planet with an isentrope if ramp compression was purely isentropic. But we really need to know how far we are from the isentrope to make these claims. Now, for shock compression, we know that when we shock a material, we generate states that are well characterized by the Rankine-Hugoniot equations. There is very good agreement between the measurements and the simulations, and there are actually temperature measurements there that we can compare. But for ramp compression, as we mentioned, the temperature measurements are often not available. So that is what motivates us to build this model from ab initio simulations to basically predict what the temperature will be in a ramp compression experiment. The main idea behind our model is that ramp compression should be similar to multiple shocks in the following sense. Let's imagine that we have the principal Hugoniot of a certain material and the Rayleigh line that connects the initial and final state. Then the heat generated in the shock should be the area between these two lines. But if we're able to break this shock into two with one intermediate shock, then the total heat generated is smaller, and we are able to reach the final state but at a smaller temperature. Same pressure but with smaller temperature. So ramp compression is similar to a series of consecutive shocks that come right after the other, and this is what we will try to imitate with our simulations. We will start with a sample that is isotropically compressed in hydrostatic equilibrium, and then we will uniaxially compress from this state to a new density. So we will perform a uniaxial compression at fixed temperature to a new density, but just by uniaxial compression. And this state, this new uniaxially compressed state, will always have higher energy than a state that has the same density and temperature but is isotropically compressed. So there's an energy difference between the uniaxial and hydrostatically compressed state. And what we claim is that is this stored energy what is used by the material to reach its new temperature. So we will provide this energy difference to heat the material that has been isotropically compressed at the same temperature and density. Okay, so the kinetic energy, we will modify it by adding this extra energy to reach a new temperature, which will be our prediction. So this is a summary of our model. We start with an initial state at a certain temperature and density. We compress both uniaxially and hydrostatically to a new density. We compute the energy difference between these two states, and we add that energy difference to the hydrostatically compressed state that will result into temperature. So let me show you how our model works for 3 steps. We will start with diamond at ambient conditions, and we will take it from 0 to 800 in 3 steps, from 0 to 200, then to 400, and then to 800 GPa. This, in principle, should reduce the overall temperature because the total heat delivered to the sample should be smaller than one shock on the Hugoniot. So this is how it looks like. We start at ambient conditions, compress to the next density, uniaxially and isotropically compressing the sample. We get the energy difference and we heat up. Then from this point, we do another uniaxial and hydrostatic compression, calculate the energy difference and heat up. And then the same thing in the 3rd step. And as you can see, the resulting temperature here, which at this density corresponds to 800 GPa, is way below the Hugoniot temperature. So we are approaching something that is closer to the isentrope and definitely below the Hugoniot, which validates our model. But how can we be certain that our model is valid? We do not have temperature measurements available to compare our predicted temperatures. So the next thing that we can do is to actually calculate the MULTISHOCKS curve. So this is what we did. With the equation of carbon that we have a bunch of simulations at different temperatures and pressures, and we can solve the Rankine-Hugoniot equations to derive the principal Hugoniot curve here in black. Then we choose one state along the principal Hugoniot as the initial state for the next shock, and we derive the secondary Hugoniot curve. Same for the 3rd, 4th, 5th Hugoniot curves, and the collection of these states basically are the MULTISHOCKS curve. So when we compare our results with our model, this multi-shock compression model with our uniaxial compression model, this is what we obtain. As you can see here, our model in the blue line agrees remarkably well with the MULTISHOCKS predictions, which is our way to validate the model that we have proposed. What we also did was to compare the predictions of our model with a recently proposed model by Damien Swift et al. In PRB that is based on plastic work heating, and our predictions agree with them if we assume a Taylor-Quinney factor of 0.25. This Taylor-Quinney factor was the same that was used in the experiments reported by Amy Lazicki to get a temperature in these experiments, but the fact that the Taylor-Quinney factor that is used to account for plastic work is so low means that just 1/4 of the plastic work energy goes into heating the sample. That means that either diamond is weaker than we thought, or that 3/4 of the energy get absorbed into vacancies or some sort of defects. So to conclude, we have demonstrated that the model that we have proposed matches really well with the MULTISHOCKS experiment, and also with this model proposed by Damien Swift et al. With a Taylor-Quinney factor of 0.25. There are still discrepancies between the experiments and the equation of state of diamond that we have to resolve. But so far our calculations indicate that these energy differences between the uniaxial and hydrostatic state match really well with the plastic work energies used in these models. And to finalize, I would just like to advertise special issue that we are preparing on the journal Minerals that is called First Principle Simulations of Minerals, and I just invite you to submit if you work on this subject. Thank you very much.